Welcome. Here we go. This is the first lesson of chapter 7, um, which is about sampling distributions. So, the first context, well, is that what is the average for the chapter 6 test, which you just took? Um, and today, if I was in school, but I'm not, we would be doing this as an activity. So I'm just going to walk you through it. We're going to be taking a sample from the population of my classes and their Chapter 6 test scores. We're going to use the average from the sample to estimate the average for the population. And this is really the idea moving forward, or a big idea in stats, I should say. You can never really survey or take the entire population, or there are many situations where you can't in real life. So you have to get the average from a sample and project it onto the population. So in one small school, there were only 5 students who took the Chapter 6 test. And one kid got a 60, one got a 70, 80, 90, and 100. Okay? Um, what if you could only sample 2 of the scores? Go ahead and do that. Pause the video, pick 2 scores, and find the average, like 60 and 90, for example, and then add them up and divide by 2. Okay, I'm going to pick 70 and 90. Okay, uh, some of you probably doing that in your head, but 70 plus 90 is 160, so the average is 80. So based on that small sample, I would say, well, it looks like the average of the entire class was 80. However, that's just my sample. You probably got something different, unless you, by chance, had the exact same 2 test scores. What are all the possible samples of size 2? And calculate the mean for each one. Now, each sample will give you a different approximation for the mean. So first you could have 60 and 70. You could have 60 and 80. Let me do all the 60s first. 60 and 90, or 60 and 100. So I'm just pairing up 60 with all the others. And then you can do those averages. Um, well, I can do that, some of that in my head, right? I don't need no stinking calculator. There's the first one. So the average would be 65. This one, the average would be 70. 60 plus 90 is 150. Divided by 2 is 75. And 80. So you can see here, these are just marching up by 5. Now that's not all the possible samples. I took care of 60. Now what about 70s? I could have 70 with 60, but I already got that one right here. But I could have 70 with 80, 70 with 90, and 70 with 100. Add them up, divide by 2. That's 75. This one would be 80. This one would be 85. All right, that takes care of my 70s. I've paired 70 up with all the others. Now about 80. 80 can go with 90 or 100. 80 and 90. 80 and 100. That's 170 divided by 2, which is 85. This is 180 divided by 2, which is 90. And then the last one is 90 and 100. The last possible sample of 2. And that would give you an average of 95. So these are all the samples. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 samples of size 2. And they give different approximations for the average. So what I've done here, right down here, is I have made a dot plot for all of these means. So 65 is that dot right there. There's only 170 right there. There were 2 75s here and here, okay? There were two 80s, two 85s, one 90, and one 95. This is nice and symmetric, right? Right down the middle, you've got symmetry. We call this the sampling distribution of X bar. These are the X bars we have received from our sampling distribution, or distribution of samples. And this is a new vocab word for the chapter. Okay. All right, number 4. What is the actual mean score of all 5 students? Well, let's add them all up. 60 plus 70 plus 80 plus 90 plus 100 divided by 5 is 80. Now, I used all the students, so that is a population mean. That is the actual population mean. It is not an estimate. It is mu, which is the population mean. Okay, which makes sense, right? They all center here at 80. There's symmetry either way, but 80 is the center. All right, well, that was a class with 5 kids. Only 5 kids. What if we had a more normal thing? Like, what if you had like 40 kids who took the test? In fact, I had 130 kids take the test. And here's their scores. Student 1 got a 60, student 2 got a 79, and so on for all 40 kids. Here's what I want you to do. Number 5. Take a random sample of 5 scores and find the mean. You can take a random sample of 5 however you want. You could do every I don't know, 7th kid. You could get out a random number generator and do it that way. Where was that again? Math, probability. There it is. Random integer on the side here. I could do a random integer 1 through 40 and just start doing this. And those are the people I would pick. The 34th kid, the 16th kid, and the 32nd kid. So you can pause it right now, take your own sample, and then hit continue when you're ready to move on. For me, I might as well just use these numbers. So 34, I'm going to use, so where's that? 34 is this person. 16 is this person. 32nd is this person. 32nd again, I'm not going to do the same person twice. This is without replacement. 37 up here, and 8. So those are my scores that I'm going to use. I'm going to write them down in order. 71, well, order doesn't really matter. 89, 99, there's a good score. 82, and 86. I'm finding my average now. Divided by 5. So I got 85.4. Okay? Now, if we were if I was in class today, I was going to have a post-it up, or a big poster paper up on the board, and I was going to have each one of you take your answer and put it on the dot plot for the entire class. So each of you took a sample just now, your own sample, right? Yours is probably different than mine, most likely. So then I was going to have you come up and put your dot there. So if you got like an average of 73, you put your dot. If another kid got a 74, they'd put their dot. And I was going to have all my classes do this. So instead, I have just kind of made it up. Let's say Jimmy came up and put that dot. Then Carly came up and put this dot. And then this was Cooper's dot, and so on, right? This is 29 dots. Okay? So this would simulate a class with 29 kids. Each took their own sampling distribution and put the dot for theirs on here. Okay? So the highest average we ever got was 90. The lowest average we ever got was 73. Okay? And then here, what is the actual mean score for all 40 kids? Meaning add them all up and divide by 40. Whew, so don't take a sample of 5. Actually do the entire population. Well, I've already done it for you. And I got 82.1. Okay? And again, since that's all 40, that is the population mean. And does it kind of make sense with our numbers up here? looks to me like 82 is pretty much in the middle. It's not perfectly symmetric, but it looks pretty decent. Okay, so we took a sample to try to estimate the population mean. Okay, my sample here, this is my X bar, which is a sample mean. Okay, and then when I used all of them, it's called mu, which is the population mean. Okay, what I'm getting at here is some of these big ideas. Okay, bye bye calculator. Is here. If you know the whole population, you are finding a parameter. So let me try to translate that up here. This is a parameter because it's the whole population. Okay. If you have a sample, zoom in on that. Samples give you statistics. Think P and P and S and S. Okay. Samples give you statistics. So this 85.4 came from a sample. So it's a statistic. The statistic is trying to describe the population. Okay, so there's statistics over here, which are X bar, P with a little caret, we call that P hat, and standard deviation of the sample. As opposed to parameters, we have mu, which is the population mean, P, which is the population proportion, and sigma, which is the population standard deviation. Um, so just keep these two differences in your mind. Target number 2 is a sampling distribution. This is the values for the statistic for all possible samples from a population. Now, this is 29 possible samples right here. We had 29 dots. Is that all the possible samples? No. So I guess it would be wise to do more samples, but at the same time, it's not ever really realistic to do every single possible sample. At the top, we did right here. There were 10 different samples. That was quite reasonable. We could just write out all 10. You could graph all 10. So this is a sampling distribution of all 10 samples. Okay, so when possible, do all the samples if you can. And learning target 3 is are your results statistically significant? Count the dots. If it's less than 5%, it is significant. Like, meaning if you count, there's 29 kids here. What's 5% of 29? Well, 0.05 times 29. 1.45. Okay, so if I had that's 1.5 dots. I'm thinking like if you got an average less than 74, is that significant? Well, to be significant, it should be less than 1.5 dots where that occurred. So I wish this number was nicer, like say 1 dot. Let's just say it was 1 dot. We'll scooch this over. That meaning if you did get a sample with this result, 73 in this case, it is less than 5% of this overall curve, of this overall distribution. So this outcome would be significant. Likewise, this outcome on the top, 90 or higher, would be like roughly would be less than 5% of all the sampling distributions. So that would mean like if you took a sample and you got an average of 90 or higher, that only happens about 5% of the time. So that is quite significant. Okay. Um, we'll chat through these. Next one's how cold is it inside the cabin? During winter months, outside temperatures at the Sternice's cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mr. Stern sets the thermostat to 50. The manufacturer claims the thermostat allows variation in the home temperature that follows a normal distribution, and sigma is 3. So, to test the claim, Ms. Starnes programs her digital thermostat to take in a simple random sample of 10 readings during a 24-hour period. The standard deviation of the results is Sx of 5 degrees Fahrenheit. So, we're just identifying population, parameter, sample, and statistic, okay? So remember, P and P go together, and S and S. And I've already got the answers listed here. Let me just explain them to you. The population is all the possible times during a 24-hour period, okay? Because he set it to a 24-hour period. The parameter is sigma, which is the true standard deviation of the temperatures at all possible times, okay? They're claiming that this is 3 degrees Fahrenheit, okay? The sample, what was the actual sample? They took 10 random times, a snapshot, 10 random readings. That is your sample. The statistic is what were the sample's results? That was right here. Remember S for statistic, right? All the readings came back with a standard deviation of 5. The population parameter was 3, but the sample came back as a 5, which seems quite a bit bigger, okay? Suppose the thermostat is working properly and the temperatures vary according to a normal distribution with a mean of 50, like it was saying, and a standard deviation of sigma of 3. The dot plot shows the distribution of a sample standard deviation in 100 simulated SRSs of size 10. Okay, let me break that down. This is 100 dots. What is each dot signifying? Each dot is a simulated random sample of 10. They pulled 10 readings from this thermostat, averaged them out, found the standard deviation, and plotted the standard deviation right there. They did that again for all of these dots. Every single dot is the result of a sample of size 10. So this is a lot of data right here. Okay, it's 100 dots. Each dot represents a sample of 10. So it's actually 1,000 readings that were taken. And what we're actually plotting here is the standard deviation of the sample. So in this first sample of 10, it looks like the standard deviation was about 1.25. Say over here, 4.6 would be the highest one they got, okay? And these ones in the middle were 3.0. And they're claiming that if it's working properly, it's 3 degrees in the middle. Okay, so that's what that chart means. So if it's working properly, you get this kind of distribution. All right. But when this person up here took their sample, these two this and this, they're not really connected, okay? This person thought theirs was busted, so they did this random sample and they got 5. Someone else here had a working thermostat and they took 100 samples of size 10 and got all of this, okay? So, number 2, would it be unusual to get a sample standard deviation with Sx equals 5 or greater, with a size of 10 when when the standard deviation is supposed to be 3? And the answer is yes, because they did that 100 times, right? They did a sample of size 10 100 times. Did they ever get this result? Did they ever get a standard deviation of 5? Not once. So, would it be unusual? Yes, for sure. In 100 simulated samples, each sample's 10 readings, none of them were up here at 5. So essentially, based on this simulation of 100 samples, the probability of having a standard deviation above 5 never happened. So 0 out of 100 tries. So this is just a good way to think about this. 3, last one. Based on the actual sample, and your answer to question 2. Sorry, the actual sample is this one. This is their sample up here. Based on their sample and the answer to question 2, is there convincing evidence that their thermometer is more variable? More variable means, when I read that, I think higher SX, higher standard deviation. Does it have a higher standard deviation than the manufacturer claims? The manufacturer's claim is sigma. They're claiming 3 degrees. Their claim is like the population parameter. Okay. Then here, S is what the sample came up with. SX got 5 degrees. Okay. So here we're getting into the details of the population is expected to be this, but our sample came back with this. And is that significant? Is there convincing evidence that the thermometer is higher than it's supposed to be? Explain your reasoning, okay? And we've kind of talked it through here, right? They got a 5. And look down here. That never, ever, ever happens, okay? So I would say yes. Is there convincing evidence the thermometer is more variable? Yep, because it's not likely to get a sample standard deviation of 5 degrees or greater by chance alone. In fact, in 100 samples, it never happened, okay? So it's quite convincing evidence that their thermostat, their thermometer is broken. It's not keeping the temperature in the house as steady and as constant. It's fluctuating up and down too much, which makes the standard deviation larger. All right, a lot of deep thinking today. Thanks for listening. Button up these notes, and you're all